So in electron microscopy, we throw a beam of energetic electrons onto our sample. Now in the sample, these electrons scatter, and they may undergo interactions with the material, and ultimately some of the electrons may escape, secondaries or backscattered or forward transmitted electrons. Now if our sample is perfectly conductive, nothing will happen to that sample. But if our sample is non-conductive, or some parts of the sample are non-conductive, the sample or parts of the sample may charge. So now we'll just briefly look at what happens if a sample is charging. And in this case, we will look again at scanning electron microscopy. So say we have a sample here, and on that sample we have an incoming electron beam here. So this is the primary beam. It has a current I, so the number of electrons per second, and a specific energy, E0, the energy of the incoming electrons. Now in the sample, electrons may escape from the sample. So this may be the backscattered electrons, for instance, and it will also be a certain amount of electrons per second. So we have an affiliated current, which we call the backscatter electron current, so I, B as E, and depending on the incoming electron beam current and the yield of second backscattered electron creation, this will be a certain factor, which we call eta, times the primary beam current. And in this case, our eta is what we call the backscatter electron, or B as E, yield. Yes, on the other hand, we can also have secondary electrons exiting from the sample, and equivalently we will have an associated secondary electron current, which also will be a certain constant, which we call delta, times the primary beam, incoming primary beam current. And now the delta is what we call the secondary electron yield. Now we see that if eta plus delta equal 1, no electrons will be net deposit into the material. So the amount of electrons going into the material is equivalent to the amount of electrons going out of the material. Of course, if eta plus delta is smaller than 1, so the sample may charge negatively. So it will undergo negative charging. If eta plus delta is larger than 1, the sample may positively charge, as more electrons escape from the sample than that are ejected. So, and again, if our sample is conductive, this imbalance will just be counteracted by a current going to or from the sample, and nothing net will happen. But if that's not the case, our sample may charge. So let's look first at the case of negative charging. So here, eta plus delta larger than 1. So again, I draw my sample here. Now we have our incoming primary beam here, IP, and while the primary beam is striking on the sample, it will negatively charge. So here is the positions where we have already been, leading, so this beam is scanning in this direction, leading to negative charging. So in this case, the incoming electrons will feel this negative charge, and the beam will be decelerated, and the extent to which we will be sensitive to the deceleration, of course, depends on E0. The charge build up here initially may be quite small, so if we have a high energy here, 30 kV, the deceleration may not be that pronounced. If we have a very low energy, 1 kV or smaller, actually the deceleration may also be pronounced, and the incoming beam may hit the sample with an energy substantially lower than E0. But in any case, in this case, the incoming electrons will feel this negative charge, and they may be deflected, and thus hit the sample on a different position and generate signal from a different position than where we think we would be. Also in this case, if this beam does hit the sample, the secondaries that escape from the sample here will be accelerated by this field and thus hit our detector with a higher energy than what we have. So the signal may actually be brighter because maybe more secondaries or higher energy secondaries are ejected from the sample. Now, of course, in an extreme case, if the sample would substantially charge and the field buildup here will be higher than the incoming electron beam potential, the electron beam may also just deflect fully. So in this case, the electron beam will travel into the vacuum chamber and may actually hit parts of this chamber, the pole piece of the electron lens or parts of the detector, and generate secondaries there. In that case, we may get a signal that resembles, while we are scanning, the interior of the sample chamber of the SEM. So then we get an image that is a mirror of the inside of the electron microscopy chamber. This is a fun experiment to do if you look at a non-conductive sample, and you can really get like a photograph of the interior of your SEM. Now the other situation, of course, is where we look at positive charging. So in this case, eta plus delta larger than 1. Again, we have our incoming electron beam here with energy E0. We have our scanning beam that charges the sample positively. And in this case, of course, the first thing that happens is that any secondaries that may want to exit the sample will be pulled back towards the sample. So less secondaries may be emitted from the sample than if there was no positive charging. So typically this leads to a darkening or a blackening of our image. Also, if the primary beam now is attracted to the charged area, so the energy may increase in this case, and we've seen a negative charging that it may decrease. In this case, the primary energy may increase a little bit, and it may also be deflected towards the area that is charged. So this may lead to appearance of streaks of dark areas on the sample, a typical sign of positive charging. Now finally, let's look at how this picture looks like as a function of electron beam energy. So I'm going to draw again a graph. So here we have the horizontal axis on which I will put the primary beam energy, the incoming primary beam energy, and on the vertical axis here I put as our variable delta plus eta, so the total electron yield, the sum of the secondary and backscattered electron yields. Now for typical materials, if we look at how this curve looks like, of course the value that is important is where delta plus eta equal 1. So that is a line in the graph here. So this is 1. A typical curve will look like this. So at low energies it will quickly rise above 1. We'll have a regime in energy space where the total yield is higher than 1, and then decrease when we go to higher energies. So if we now look at this graph with this picture in mind, we have a regime here at very low energies where the sample may be negatively charged. Again, if we have a non-conductive sample, then we have a small regime where we have positive charging between two energies here, which we call E1 and E2. This is a bit of bad E, but I think you understand it's an E, E1, E2. And then for energies higher than E2, of course, the sample will negatively charge in all this regime. So typically, this point of E2 is important. It typically has a value of around 1 kV for most materials. And the importance here lies in the fact what happens if we have energy slightly lower or slightly higher than E2. And so if we end up with an incoming primary beam with an energy slightly lower than E2, we'll see that the sample will positively charge. So the incoming electrons will be accelerated. They will go to higher energy, and we will gradually lower the total electron yield while the energy of the beam is increasing until we hit the point of E2, where the total yield is 1 and the sample becomes stationary in terms of charging. Equivalently, if we are at slightly higher energies than E2, the sample may negatively charge. And in this case, the electron beam will be decelerated and we will gradually move up the curve, increase the total electron yield until again we reach the point where we are at E2 and the sample will not show net charging anymore. Of course, this balance is very subtle, but it gives you an idea of what may go on if we are very careful in imaging non-conductive samples.